The other day we defined a new term in the context of magnetism, and that was a domain. Not the math domain, the physics domain in the context of magnetism. Does anybody remember what that is? Even if you don't give me the exact definition, if you just kind of give me the general idea, that'd be great. All right then. It is a tiny little region inside a ferromagnetic material. That's the first big word in that definition. The word probably that makes the definition kind of tough. It's a tiny little region inside a ferromagnetic material that's represented by arrows. What's a ferromagnetic material? Good, a material that can become magnetized. Not that is magnetized, but that can become magnetized. Can you give me an example of a ferromagnetic material? What's the most common one? What's the most obvious one? Ferromagnetic material. Iron is probably the most obvious because the chemical symbol for iron is Fe. But then we've got steel as well. We've got a number of other ones as well, but these are probably the most common ones. Iron, steel, so on. Give me an example of a non-ferromagnetic material. I'm sorry? Rubber is a good example of a non-ferromagnetic material. Copper. Yeah, copper's a good one because we kind of get this thought sometimes that things that are metals, they're good conductors of electricity, and they're also ferromagnetic materials, things that can be magnetized, but not necessarily. Okay, most metals are very good conductors, but a lot of them are not ferromagnetic, so they can't become magnetized. So we got copper, we got rubber, we got glass, and all of those insulators are not ferromagnetic either. So it's a tiny little region inside a ferromagnetic material that's represented by an arrow. Remember, it's not really an arrow. We simply represent it by an arrow. Might look something like this. You get arrows pointing in, well, it looks to be more or less random directions. These domains pointing in seemingly random directions. By the way, is that a magnet or just a ferromagnetic material? Yeah, that's not magnetized, right? It can become magnetized because it's got these little domains that are pointing in certain directions, but it's not magnetized right now because they're not pointing in the same direction. So let's take those domains and let's try to align them. Let's try to get them pointing in the same direction. What's one of the ways that we can do that? One of the ways that we can get these things changing direction and pointing at least more or less in the same direction. Bring another magnet nearby. In fact, the closer you bring it, the better. In fact, if you rub it against it, it's even better. Okay? This other magnet has to have its domains aligned already. The effect of this magnet nearby will be to cause these domains to become at least more or less aligned. Right? These aren't all exactly in the same direction, but we have a magnetic effect now because they're not canceling each other out at least. They're kind of in the same direction. They're more or less in the same direction. What's the other way to do it? Jesse? Yeah, wrap it in wire. You get a wire going around it. Of course, it's not just enough to have a wire going around it. The wire in itself does nothing. But if you attach something to the wire, then that's going to work. Jesse, what do you have to attach to the wire? No? Electricity, a battery or power supply of some type. When you have any electrons or electricity flowing through a wire, that generates a magnetic field. And if we have them wrapped up like that, then the magnetic field actually gets generated by each section of the wire, each loop of the wire in the same direction. We'll learn more about that next week. But that causes the domains inside this ferromagnetic material to start pointing in that direction that the magnetic field points caused by this wire. All right? Yeah, go ahead. That's a good question. Good question. If only half of it was wrapped, would the whole thing become a magnet? The answer is, to some extent, yes, but not as great as the section that was wrapped in the wire. So if you've got, let's say we extended this way down here, you would get some magnetic effect down here as well, but it would be a stronger magnetic effect in this portion of the magnet right there. All right? We talked about magnetic fields as well. The magnetic field surrounding a bar magnet, let's say, I'm not going to draw the polarity of it. I'm just going to draw the shape of the magnetic field surrounding the bar magnet. You're going to tell me what the polarity is. Okay, we've got magnetic field pointing in this direction. Which end is north? Which end is south? North. The left side is north? Why do you say that? Yeah, the magnetic field lines go away from the north and toward the south. Good. By the way, if I cut that in half, would I be left with a north magnet and a south magnet? No, I'd have a north and a south and a north and a south, and the magnetic field surrounding each of those would look like the magnetic field surrounding that one. What if we have two magnets here now? Tell me, first of all, whether these magnetic poles are like poles or unlike poles. In other words, north against north, south against south, north against south. Like poles or opposite poles? They're like poles. How do you know that they're like poles? The field lines go away from each other, right? The shape of the field tells us that they're like poles. We know that one of those laws of magnetism was like poles repel each other. Unlike poles attract, like poles repel each other. What is the polarity then? Okay, we know that they're either north and north or south and south. Which one is it? Why do you say it's north and north? Because the field lines are going away from it. Good. That end must be then south, and obviously this one's going to be south as well. Good. All right, the third one and final one, I mean, you can take a guess probably right now that one's going to be north and one's going to be south. The shape is going to look like this. One is north and one is south, but which one's which? Is this one north or is this one south? North or south? First one is north. We know that again because the direction of the field lines go away from north and toward the south. It's like the electric field lines going away from positive and toward the negative. It's not the same thing because we're dealing with magnetic fields, but it's like that. Yeah, Josiah? Yes, yes, they are. Thank you. I did that on purpose, just to test you. Josiah, thank you. You passed. That is a south. You're absolutely right. Okay, if you get a diagram, I didn't make that mistake on purpose, obviously, but I'm glad I did make the mistake, even though it wasn't on purpose. Sometimes we get on a diploma exam or on a unit test, as you saw in your electricity unit test, you get this diagram that shows electric field lines or magnetic field lines, and you have to identify which one's correct. Okay, if they label this, and they do exactly what I did, but they do it on purpose, you have got to be so careful there. You've got to be so careful. This is an easy question to identify which diagram is correct if you're careful. Okay, but it's so easy to look at this and say, oh, okay, north and south, the shape is right. Oh, it looks like the field lines are going from north to south, but oops, south to north. This one's wrong, right? Okay, so make sure that if you do get something like that on an exam, a test or an exam, that you recognize the mistake there, that those are going from south to north, and that can't happen. They always have to go from north to south. Okay, I doubt, to be honest, that they would try to trick you that badly. Okay? If they put the field lines wrong here, they would probably put them wrong everywhere, as opposed to just in that one place. But be prepared for that just in case. Okay? Good? We defined the direction of the magnetic field, right? This is stuff you wrote down the other day already. We defined the direction as from north to south. Okay, we just talked about that a minute ago with the field line diagrams. But we also defined it as the way that a compass needle points, the way that the north end of a compass, right? That red tip of the compass needle is the north end of the compass. It's the way that the compass needle points when placed in that field. We did the lateral activity the other day where we put the compass in the magnetic field. That showed us the direction of the magnetic field. Hence, we define the direction of the magnetic field as the way that the compass needle will point when placed in that field. Just like the electric field is the way that a positive particle will move when placed in the field, just like a gravitational field is the direction that a mass will move when placed in the field. But we also define it as being from north to south. Now, if you look closely at these two definitions, there seems to be a little bit of a conflict in them. Draw a picture of the Earth here for a second. The Earth is made up of rock and dirt and organic material and molten magma deep within the Earth. And that molten magma swirls around, and as it does that, it creates a magnetic field. And the magnetic field that permeates the Earth looks like the magnetic field that surrounds a bar magnet. Now, it's a weak magnetic field. It's a very weak magnetic field, about 1,000 times weaker than the magnetic field around an average bar magnet. That's why when you bring a compass near a bar magnet, it isn't affected dramatically by the Earth. It's affected a lot more by the bar magnet than it is the Earth. It's a weak magnetic field, but it's still a magnetic field, and it looks like the magnetic field that surrounds a bar magnet. So it looks something like this. It's as if there's a bar magnet inside the Earth with a magnetic field that permeates it around that so-called bar magnet, create a magnetic field around the Earth that looks something like that. Now, let's draw a picture, draw the equator right here. Let's draw that in black. Say this is the equator. Let's say you're standing on the equator right here with a compass. Which way is your compass going to point? Which way is it going to point? It's going to point up, right? It's going to point towards Canada, right? Towards northern Canada, towards the North Pole, right? How do we define the direction of the magnetic field again? We defined it as the direction that a compass points when placed in the magnetic field, but we also defined it as from north to south. What does that mean? Here's what that means. It means that the magnetic North Pole is not really where we think it is. The magnetic South Pole is where we think of as the North Pole. Now, geographically, the North Pole is exactly the way we think of it, northern Canada. But magnetic North Pole is not northern Canada, rather it's Antarctica. The conclusion that we can draw from this is inescapable. The conclusion that we can draw from this is that the penguins don't live in the South Pole. The penguins live in the North Pole. And this is why you had so much trouble finding Santa Claus when you went looking for him as a little kid. He doesn't live in the North Pole. He lives in the South Pole. Geographically, it's still the same. Okay, Santa Claus lives in the North Pole geographically. But strictly speaking, magnetically, it's not the North Pole. It's the magnetic South Pole. Now, when we navigate, when we use a compass to navigate, we call it the North Pole still. We still say northern Canada is the North Pole. It's just not. But that's okay. As long as we all use that frame of reference, it doesn't really matter if it's correct. It's a name. It's a name. We could call it Eduardoville if we wanted to. And as long as everybody called the North Pole Eduardoville, then it really wouldn't matter because we'd all know where we're going. So despite the fact that we call it the North Pole, magnetic North Pole, it doesn't really matter that it isn't because we're all calling it the same thing when we're navigating. Does that make sense? Strictly speaking, though, and understand this, okay, although we call it magnetic North Pole, it isn't. It's geographic North Pole, and it's magnetic South Pole. And, of course, on the other end of the spectrum is, here we got, down where the penguins live in Antarctica, we've got magnetic North Pole. We have geographic South, but we've got magnetic North Pole. Does that make sense? So you go home from school tonight, mom and dad say, what'd you learn at school today? Learn that Santa Claus doesn't live in the North Pole. He lives in the South Pole. Exactly. That's why when you go out when you're a little kid, when you're 6 years old and you go out looking for Santa Claus, that's why you can't find him. Because you're going to the wrong place. Sorry? Yes. Go to the South Pole. Now, you don't need to copy down this table here. This is just for perspective, okay, guys? This gives you just magnetic field strength of different magnets, of different type, different things. The units, by the way, for magnetic field, we haven't talked about that yet, are Tesla. The symbol is a B. capital B, it's a vector field, so it's going to be a little arrow over top of the B. Magnetic field strength is blank Tesla. Now, the magnetic field strength surrounding the Earth is around 10 to the minus 5 Tesla. That's a weak magnetic field, 10 to the minus 5 Tesla. Again, you don't need to know these numbers. It's just more for perspective. The magnetic field surrounding an average bar magnet is about 10 to the minus 2. So that's about 1,000 times stronger than the magnetic field surrounding the Earth. Now, the bar magnets that you guys used the other day would have been weaker, right? They wouldn't have been 10 to the minus 2. They might have been 10 to the minus 3 or so. But they were still dramatically stronger than the Earth's magnetic field. And you know that because when you brought the compass, when you had the compass away from these magnets, it pointed towards magnetic south of the Earth. But when you brought it nearby these bar magnets, it wasn't affected by the Earth anymore. It was affected more by these bar magnets. A sunspot, this activity that takes place on the surface of the sun, is about 10 times stronger than the magnetic field surrounding a bar magnet. Why aren't our compasses affected by sunspots? Well, they are, but they're not affected dramatically by sunspots because these sunspots are so far away, right? MRIs? Who's ever had an MRI here? Yes? I had an MRI on my knee once, and I was surprised when I went in to get the MRI about all the stuff they make you fill out, like all the papers they make you fill out. Obviously, there's the permission. You're giving them permission to do it, and signing away your life in case anything bad happens. But there's also all this stuff like, have you ever had metal in your eye? Have you ever, do you have have you ever had metal in your skin, or all this stuff, jewelry and all this different stuff? Why is that an issue? Why are they asking you that question? You ever had a chunk of metal in your eye? Why is that a big deal? Yeah, if it's a piece of copper, it doesn't really matter. But if it's a piece of steel that was ever in your eye, and there does happen to be a little fragment still in your eye, and they're doing an MRI of your head, then that might be a big deal, considering the magnetic field of an MRI is about 15 Tesla, which is 10 to the 1 Tesla, which is about 1,000,000 times stronger than the Earth's magnetic field. Yeah, that's a pretty strong magnetic field, 15 Tesla. My father's had an MRI. I'm not sure how he ever has had an MRI. He worked, before he retired, he was in construction and always worked in the shop as a mechanic in construction. And he's had 1,000,000 things happen to him, like 1,000,000 accidents happened to him at work. One of them, I remember, one day he was grinding this chunk of steel, and this chunk of steel broke off and embedded itself in his arm. And it's still there. I mean, you can, if you touch his arm, you could feel the lump in his arm, and you can feel this little piece of steel that's about the size of the end of your baby finger like this. You can feel this piece of steel moving around inside his arm. I'm not sure why they never took it out. But that would be an issue, right? It's steel. That would be an issue in an MRI machine. Now, his MRI was on his back, not on his arms, but I'm not sure exactly what they do there and why that wouldn't be an issue. But it was okay, but it would be a source of concern for them because steel is obviously a ferromagnetic material that's affected by a strong magnetic field. The strongest human magnet? Well, this gives you perspective as to the strength of the MRI machine. The strongest human-made magnet ever made is only about twice what an MRI machine is. So it's the same order of magnitude, only about twice the value of the MRI. Here's what you want to stay away from, though. Stay away from one of these magnetic neutron stars, because they have a magnetic field that's 10 to the 11. That's pretty strong. Now, I don't know this. I'm only making an educated guess, but I would guess that besides the fact that, there's a whole lot of reasons you would die long before you ever reached a magnetic neutron star. But let's assume you could reach a magnetic neutron star and be exposed to that strong of a magnetic field. I expect that magnetic field would be strong enough that the iron in your blood would get sucked out. Literally, the iron in your blood would get sucked out of it. Okay, you have iron around in your blood, right? Biology people will know why a lot more than me. I think it's something about carrying oxygen or something. Oxygen or something, yeah? Okay. It's iron. Like it's the same thing. Iron is Fe. It doesn't matter whether it's in your blood or whether it's in the ground. It's iron. It's Fe, and it's ferromagnetic. So I would expect when you're dealing with a magnetic field strength that's this strong, you probably, well, if you didn't die for a million other reasons first, you'd suffocate because all the iron would be sucked into your blood, and then whatever that does to your oxygen. Well, there you go. Then it wouldn't transport it into your body. There you go. You gonna have a brain aneurysm? All right. All right. The good news is you'd be dead before that happens, so you wouldn't feel that. Okay. Let's compare the field strength, the fields that we've talked about so far. Okay. We've got gravitational, we've got electric, and we've got magnetic fields. Gravitational field. Let's look at the sources. Okay. The gravitational field is a field that's caused by an object with mass. Electric field caused by an object with charge. And a magnetic field, I don't know why I wrote this down like this, a ferromagnetic material with aligned domains. What's an easier way of saying that? What's an easier way of writing what I wrote down right here? A magnet. A ferromagnetic material with aligned domains is just a magnet. But doesn't it sound smarter when you write it like that? You can just write down a magnet if you want. I'm not sure why I wrote it down like that. How do we define the direction? Well, gravitational field is always attractive, and it's always toward the producer. It's always the way that a mass, an object with mass will move when placed in the field, which is going to be, of course, toward the producer. The electric field is attractive or repulsive. The direction of that field is away from the positive, and it's toward the negative. It's the way that a positive particle moves when placed in the field. And the magnetic field is attractive or repulsive again. It's away from the north. It's toward the south. It's the way that a compass needle points when placed in the field. The north end of a compass needle, by the way, which is the red tip of the compass. So why do you see a map up on the board? Well, because I like this map. Treasure map, treasure's right here. Let's say you're a guy almost 200 years ago named Hans Christian Ørsted. And let's say you're looking for a buried treasure. You've got a compass, and you're looking for a treasure on this map. Okay, and the compass is pointing towards, well, we now know it as magnetic south pole. And then let's say you flip on an electric current. Okay, you've got some kind of electric current flowing for whatever reason. And all of a sudden, your compass doesn't point in the right direction anymore. Your compass points in some other direction. And then you flip off the switch, and your compass points where it's supposed to point again. And then you flip on the switch, and it points in some crazy direction again. And then you flip off the switch, and it goes back pointing towards magnetic south. And then you change the wire. You move the wire, and you turn on the switch, and now your compass points in a completely different direction. And so on and so on and so on. What's your conclusion from that? What's your only logical conclusion from that? Someone's messing with you? Okay, what's your other only logical conclusion with that? Okay, what's your only other logical conclusion from that? Yes, there's a relationship between electricity and magnetism. In fact, we can take that a step further. If this compass is affected by an electric current, then that electric current must be generating a magnetic field. That was the discovery of Hans Christian Ørsted in 1819, that there is a relationship between electricity and magnetism. And that relationship is that electricity generates magnetism. That's why when you wrap a wire around a ferromagnetic material and you apply an electric current through it, then you're going to make an electromagnet. 1819. This is almost 80 years before the electron was even discovered. We knew about electricity in 1819. We just didn't know what it was. We just didn't know that it was electrons flowing. We knew that there was electricity, and we knew after 1819 that that electricity generated magnetic fields. And we knew that it would affect compasses, and we knew that it would affect other magnetic fields. We just didn't know exactly why. we're going to wrap it up there for today. On Monday, you're going to learn how to determine what that magnetic field looks like surrounding this wire that has an electric current in it, what the shape of it is, what the direction of it is, how we can find the interaction with other magnetic fields. Right? That's it for today. Have an epic weekend.